cancer biology, nanotechnology, and occupational health domain of science. He is the recipient of Young Scientist Award from International Union of Radio Science General Assembly, Toronto, Canada in 1998. Besides this, he has widely published in this domain, as well as he is editorial board of many prominent journals which are publishing in this domain. So with this, I like to invite Professor Raj Rajamani for an introductory remark of this day. Please, sir.
Thank you, Dr. Usha. Distinguished speaker of the day, Professor D.M. Banerjee, Center for Advanced Study in Geology, Delhi University. Dr. Usha, the Envis co-coordinator, JNU. Ms. Swati, Program Officer, Envis Center, JNU. All our faculty colleagues, our Envis team, my dear students, friends, ladies and gentlemen. It's a very good morning to all. I feel extremely happy and honored to welcome you all to the webinar on the occasion of National Science Day. In one of my class, I asked the student long back why we celebrate the 20th February as a National Science Day. Many of them did not know why. As Dr. Usha correctly said, just for the National Science Day celebrate. Most of the people, students, may not be aware of the National Science Day, why we are celebrating it, as Usha has clearly mentioned. So every year, the government of India provides a theme for the Science Day. As this year, the Science Day is the theme for Science Day is integrated approach in science and technology for future for the sustainable future. Now, the recent years we had witnessed a number of climate-induced disasters, global warming, energy depletion, economic issues, which led to realization among us our future. We now know that there is a limit for the carrying capacity of our planet. We cannot continue our business as usual without reaching no return to the future humanity. This process led to a concept called sustainability. Now, what is sustainability? Everybody know that. But still, there's a proper definition for this sustainability. It is the meeting the needs of the present without compromising the ability of future generation to meet their own needs. So this is the sustainable development, the definition given by the Brundtland Friendline, right? Book it is given. So everybody, the planet can meet the needs of every person, but not their greed, as it says. So every person, his need is met. Sustainability is the key to the solution for the problem which we are facing today, day-to-day life. Like there are ecological, economical, societal problems. Pillars for the sustainability, that is economic, environmental, and social sustainability there. So the environmental sustainability, as the environmental science students and the colleagues and scientists, we have a role to play in environmental sustainability. That is one of the main pillars, 3 pillars. It is all about operating in a manner that protect the climate and national resources for the future generation. And now, I'm very happy that this year, science and technology integrated approach will help to protect these sustainability. So science and technology plays an important role to address this issue, that innovation through science and technology will help us to meet the needs of the present without compromising the ability of the future generation's own needs. How can we do it? We can develop a new innovative idea to conserve the natural environment resources, minimize the negative impact on human activities. In addition, what we can do is reduce the energy we consume, reduce the waste we generate, reduce the material we use in producing some new materials. These are things we can do it from our side. In addition, the green technology development will help us to achieve these zero emissions, zero waste, zero discharge. We can do it. That is possible with you and us. Only the new student, the young scientist can able to do it, and science and technology will help in that way. The green technology, there is a promising future in meeting these needs of sustainability. Our research, I want to emphasize here to the young research scholars. Most of them are research scholars here. So I want to emphasize here the research, our research and development should not be stopped within the four walls of our lab, so-called lab or room or office. But it should develop such idea which will be used for protecting our environment and the natural resources for the future. So our research publications, everything is good, but it should reach to the natural, to come to a point where it protects our natural resources, national interest. I don't want to take much time. I hope with this integrative approach of the science and technology will yield a fruitful future sustainable. With these few words, I once again welcome one and all, Professor Banerjee again, once again welcome you, sir, for agreeing to give a talk today. Welcome and have a wonderful talk today. Hope you will enjoy Professor Banerjee's talk and others. Thank you so much. Once again, thank you. Namaskar.
Thank you, Professor Paulraj, and thank you for enlightening our participants about why the theme of National Science Day 2022 is kept as integrated approach in science and development for sustainable future and its importance. And with this, we proceed ahead. And I would like to thank Professor Dhiraj Mohan Banerjee, sir, that he has agreed to give a talk on today's celebration, which we are organizing. But I just want to apprise all the our participants that Professor D.M. Banerjee was former head of Geology Department of University of Delhi. Sir has received his education at Lucknow University and obtained his MSc degree in 1962 and PhD degree in 1967. He served the Geological Survey for nearly 3 years before joining the Delhi University in 1970. And he carried out advanced research as a fellow of the British Council, Alexander von Humboldt Foundation, and Japan Society of Promotion of Science. He retired in 2007 from Delhi University, but he continued to work in Geology Department and later as an honorary scientist. So presently, sir is the INSA Emeritus Scientist, member of the INSA Council, and chairman of several national and international scientific committees. And he is also the member of UNESCO IGCP Scientific Board. Sir has also served as an editor and member of editorial boards of several national and international scientific journals. Sir has extensively traveled all over the globe, represented India in geological meetings and conferences, and published more than 200 scientific papers and articles in peer-reviewed journals and reports. Sir is a key individual in the organization of 36th International Geological Congress, which is held in a virtual mode, and in the going to held in the virtual mode in the third week of this month. And today, sir is giving his talk on Ashes to Ashes, the journey of being. And with this, once again, I would like to thank you, sir, on the behalf of School of Environmental Sciences as well as Jnu Envis. And now, please, I invite you to deliver your talk. Thank you very much.
Thank you. Can you hear me? But
Yes.
there's a lot of echo. I don't know.
Sir, actually you.
From two sources.
I have two things there open.
So you can mute one of them.
I'm not able to do it. I'm trying to do it, but it's not getting out.
Sir, on the speaker button, just press. Once you press again, it will unmute.
Okay.
Sorry, it will mute.
Let me go back again because it's...
Now there is no echo, I think.
Yes, I think one idea.
No, but I can't see you then.
Now, sir, it's okay.
Now, can I see you now? No, I can't see you. This...
Sir, it's fine now. No echo now.
No, Nico, no, but I have to sign it again. But where is the link?
But you are already in the session.
I'm already?
Yes, sir.
Yes.
Oh. No, it's not here.
Sir,
Let me just see. No, I think it's come. Is it okay? Now it is okay. But it's not full screen.
sir, it is a full screen.
Is it? Okay. That's fine. Okay, can we start now?
Yes, sir. Yes, sir. Please.
Okay. Thank you, Paulraj Rajamani and Usha Mina, and also Usha ji for giving my CV to the public. But there's one thing which you are missing. One thing which was missing, that I had deep association with the Environmental Science Department of JNU for a large number of years. I was a visiting professor for almost 6 years in the early 70s when we had Virendra Asthana, V. Rajamani, and Subramaniam in the faculty. So I used to teach one full course every for almost 6 years. Yeah. So my association with this environmental science is very, very old. So okay, I will start my talk following what Paulraj Rajamani has said, that sustainability is one of the main point which has been sort of declared as a topic for this year. So I will talk about an element, what we call it the phosphate, phosphorus, which is a really sustainable element which sustains life. P is one of the most important elements of the life. The DNA and the RNA they have P as the most important element into that. So I will talk about the phosphorus, and it's just hold on just a moment. I'm in a lecture, please. Don't. So I'll talk about, by title of my talk, it's really perhaps very disturbing. I'm talking about ashes. Oh, please. Don't call me, please. I'm in a talk. Okay. From ashes to ashes, because this is something very unusual type of topic. Why I'm calling it ashes to ashes, we'll come to know very soon. You know, the phosphorus has an atomic, I'm just mentioning some characteristic of the phosphorus element as atomic number 15 and mass of 30.97 is a non-metal. But what exactly happened? Why we are talking about these ashes? Next. Can I change it from myself?
Sir,
Can I change the slide?
Sir, I will do it.
No, but you have to do it fast because I have to do it quickly.
Yeah, sure.
Yeah. See, we started what happens after we die. The Hindu practice that we burn in fire ultimately leads to what happens, the ashes. And we know the ash immersion is a very important ceremony for in Hindus. Similarly, in Islamic, Christians, and other religious practices, the bodies are buried, and they ultimately what happened? It ends into soil and a dust. Again, why? The Asti Visarjan practice in Hindus involves mixing the pulverized bone ash in a river or in agricultural field. Why? Bone ash is a concentrated form of phosphorus derived from the burned and the powdered bone of the dead body. Bone ash is the ultimate death of pea, which gets resurrected in the form of crops that sustain our life. Our ancestors knew this secret. That is the reason why the ashes are thrown all over the places and in the fields, or they are put into the rivers. So what happened to that phosphorus? The phosphorus cycle is here. This is a very common, is a school boys school days caricature, where animals are here, there animals eat plant and then they get buried here and they transport everything to the river to the river into the sea, and then finally they get into a sediment and finally they form a phosphate rock here. This is the normal phosphorus cycle which you get in the class 7 or 8 school book. I'll go in little more detail. Please, next. Can I not do it myself? No.
So because we are presenting, so it
Oh,
will be from
yes.
our end.
Okay, I will do. No, what happened? What is the fate of the phosphate particle of ashes? These ash particles enter the soil. They get solubilized in a carbonated water. They undergo resolution and get transported. They reaches the sea. They reach the sea, utilized and accumulated by sea life. That means organic bodies. They utilize and make use of phosphorus to build their own life, their own body, their structure, their shell, and other things. They are all bathymetrically, chemically, and environmentally controlled. There are specific type of organism at a particular depth, particular environment, particular warmth of the sea, and particular chemistry of the water. So these three things, bathymetry, chemistry, and environment, control the type of phosphorus accumulation, the type of the way it will be involved into the life cycle of the organism. So finally, they get entombed into the sediments, and then when these sediments, then by tectonic processes, what we call the earth processes, by like earthquakes, another thing, when they are uplifted again from the sea, they return to the land, and then start again the new cycle. So this is the phosphorus cycle one. Next one. The term phosphorate is I am talking about the importance of phosphorate. Why phosphorate is important? Phosphorus is the 10th abundant element in the earth crust. It is the essential element of nutritive value. They are used as fertilizers, as a formation of phosphoric acid. They are very important host of uranium, vanadium, fluorine, and different rare earth elements. And they are used in paleoceanographic interpretations. Paleoceanography interpretations means how the paleogeography has been changed. The geography of the oceans have changed through time. Now, this is called journey of the particle. The particle starts from, say, my cursor can be seen? Can you tell me that is my cursor seen
No,
or
sir.
no?
No, sir.
No. Okay, then there is no point pushing a cursor. So from the land, by erosion of the land, by breakdown of the rock materials, there is a terrestrial input, and into the marine material, where the organic matter, the planktons and zooplanktons use them for life processes. This all happens in the photic zone, where the sun rays can penetrate. They all go down and gradually precipitate, sort of a deposit at the sea bottom, where there's a current, what we call upwelling current. Upwelling current is created because of the difference in the with the density of the water. So the currents, upwelling current carries those deep cold water having phosphorus into the shallow part, and where they get deposited, they get precipitated right from the ocean, directly from the ocean, they get precipitated. So originally the phosphorus came from the land by erosion of the land, carried all the way into the sea, then got into the deeper part of the sea, then again lifted up by the upwelling current, and then finally precipitated as a rock, as a phosphorite rock. Phosphorite. Next. Now this is a very important situation where this is what happened to the bones, the organic element, especially, and you have cells, phosphatic sheets on bone, and these phosphatic sheets gradually are filled up by element what we call calcium fluoroapatites. Carbonate fluoroapatite is the mineral which forms the apatite, which forms the phosphorus. So these are the diagrams which show that how the cells get replaced and cells get transformed into the phosphate mineral. Like you can see here, in the lower part, you can see the phosphatized cells, and gradually the phosphatized cells start moving out of it and leaving the empty micromoria. Micromoriums are left, and the phosphorus is removed from the endolithic bacteria, cyanobacteria, and algae and other things, and they are transported into the deeper part of the ocean to get deposited. Next. This is what happened in the depositional site, where the phosphate is being deposition. You can see there is the deposition. First there is a decrease in pH. When you decrease in pH, there is a solution activity, because then will be acidic environment and there will be solution. Then finally, what happened? Gradually the pH keeps changing and then increases pH. So then they started depositing. So carbonate rock, having reached in calcium carbonate, and the phosphorus, which is P2O5, phosphorus pentoxide, they all get together and they get mixed up with what we call the framboidal pyrite, iron sulfide. They all got mixed up, and then finally they get deposited in a methanogenesis zone. They get deposited as a deposit. So ultimately they form phosphorate deposits. Next. This is again the same photo to show you exactly the positions in the oceanic profile. You can see on the left side is the subaerial exposure. Gradually the grains go down. There is a high organic productivity zone in the shallower part where the phosphogenesis takes place. There is an upwelling of marine rich water, and then in a more shallower region, the phosphorites form. Next. What is the mechanism? The formation of sedimentary marine phosphorites. The mechanism is proposed. There is one, as I just told you, a direct precipitation from the water column. That is just now I showed you that the material is going up with upwelling water, and there is a precipitation directly from seawater just from there. Or replacement of a carbonate by a phosphate. There is a calcium carbonate already there, CaCO3 is there, and the calcium phosphorus, and the phosphorus replaces part of the calcium, part of the carbonate CO3, and then changes into a phosphoride. I will come to that chemistry of the phosphoride later to tell you how this mechanism takes place. And this is said to be upwelling induced. Upwelling, as you know, what we have, there is a high rain of organic matter. Then is followed by oxidation of organic matter. It ends into interstitial phosphate enrichment. That within the grains, within the element, or within the organism, the different parts get phosphatized. High pH, it leads to high pH, high alkalinity. So what will happen? You have phosphate carbonate precipitation and phosphate precipitation, and then they are modified by diagenesis. Diagenesis is a term which you use in geology for low temperature transformation of sediments. They get again reworked. Oh, I'm lecturing out. So this is, and then finally, oh please, Raut, I am lecturing. Don't disturb me. So after reworking, and then they are transported and they form phosphate deposit. Next. This is the more details of how the upwelling takes place. Upwelling, as I told you, there is a difference. There is from the lower part, from the deeper part of the ocean, the phosphate-rich water, PO4-rich water, moves up the slope. There are two situations are possible. One is when you have a low sea level stand, and when you have a high sea level stand. In low sea level stand, the phosphorus-rich water goes up the slope up because of the differences in density, and they are pushed up against the gravity. And then when it reaches the surface, where you have derived wind, the wind transports the surface water to the sea. So all entire material goes away, and then you get only phosphate deposition only on the slopes. So because of that, all those deposits which are formed in a shallow zone are of less concentration. They have less P2O5 content as compared to those which are formed in the deeper water. As you see the lower part, the phosphate-rich water goes up, and this anoxic water goes up and goes right up to the shallower part, and then is transported back, leading to a formation of a very organic rich phosphorus detritus in a large area. So all big deposits of the world are actually deep water deposits. The shallow water deposits are of lower quality. Next. So this is please back. So this is a cartoon to show you exactly how the upwelling current goes up, and then when it goes up, first you say that the glaciers are melting, and then giving water to the rivers, and they are weathering the rocks, and the rocks are transporting the different elements like phosphate, sulfate, strontium, silicon, and other things, all and halogens. All those things are good. They sort of encourage the bloom of oxygenated photosynthesis. So you have it transport, the oxygen goes out of the system, and CO2 gets trapped into this organic matter, and this organic matter goes down and forms organic rich shales at the deeper part. And the organic rich shales are rich in manganese, in iron, and there are other things. And all these materials are up, they go up into the upwelling current into the shallower part, where you can see on the upper hand side there are some vertical stacks. These are called stromatolites, the algal cyanobacterial columns. The cyanobacterial bodies, they eat the phosphorus. They use phosphorus and trap the phosphorus into their body and then form deposits. So there are many deposits in the country and in the world where the phosphate deposits are associated with the stromatolite or the cyanobacterial organisms. Thank you. Next. Okay, this is just another way to show the same system, that in what are the different depth of sea where sediments get formed. The phytoplanktons form there, and the death and decay of phytoplankton leads to organic material zones, and they produce the upwelling. Next. Now, what happened in deposition site? This is a mechanism by which it is formed. You can see there is a left side, you have a river influx. River is carrying the material from there. The dissolved inorganic phosphorus and dissolved organic phosphorus. Both of them are getting into the sea. Along with that comes the iron associated with the phosphorus. They are it leads to a primary productivity of organism, leads to a remineralization of the system. They are scavenged and then they produce the microbial mats. Microbial mats are the cyanobacteria or algal mats, what we call, and they algal mats trap iron oxide, manganese oxide, phosphorus, and carbonate. So all these material and also a mineral called glauconite, another mineral called pyrite, they all lead to they all get bound together. Therefore, most of the phosphate deposits are associated with these elements: iron, manganese, and like other things. So next, what is the distribution? How the phosphorus is distributed over the earth? The continental sediments and soils contain only 0.15 percentage. Igneous rocks which are formed by the igneous processes, by volcanic processes, by formation of the heat and the thing. These rocks, like granite, basalt, which are very commonly known now, they contain only 0.07%. Marine sediment contains 0.2%. The organisms, diatoms, echinoderm and phytoplankton, green algae and fishes, they contain enormous amount of phosphorus. Therefore, the role of organism in formation of the phosphate deposit is much more important than any other sort of you can say mechanism. Next. Now let me define a phosphorus. First define. We have discussed about the phosphorus, but we have not yet defined. Term phosphorite is derived from the phosphorus rock. The phosphorite is a dolomitic limestone or a shale with 15% of P2O5. That means if there is a phosphate pentoxide of 15% and more, then the rock is phosphorite. And if it is less than that, then we use the term phosphatic rock. That it has got some phosphatic content. They are found in very old rock, from Proterozoic rock to Quaternary rock. Quaternary, I mean, most of the people are aware of this geological column. The oldest rock is called Archean, then followed by Proterozoic, then Paleozoic and Mesozoic, and then Cenozoic. So youngest one is called Quaternary, in which we are living today. So right from the Proterozoic time, which dates back to 2.5 billion years old, to as much as few thousand years ago. So this is the phosphorite is found in all type of rocks. They occur in the form of peloids. I mean, for a non-geologist, it may be a little difficult to understand what is called peloid, but for a geologist, it's quite clear. Peloid is a rounded, sub-rounded type of material, or little elongated, oval type of grains. Ooids or intra-class occur in the form of a bed, parallel bed, or in the form of a nodule. Nodule is very common, or pebbles. They occur in shallow marine platforms, or they are formed by inputs from the river, I explained you earlier, and by oceanic upwelling. And they form by phosphorus-rich skeletal debris like bone beds that rain on ocean floor, and they could be of any color depending upon oxidation state. That is the reason why to identify a phosphate rock in a geological field or any mountain or any place is very difficult, because it can occur right from a very deep, very dark colored rock to absolutely white color. So you have all shades you can get depending upon how much oxidation has taken place. Sometimes it could be brown, sometimes light brown, could be gray. So this is a very difficult thing. Now, what happened in phosphate rocks? Phosphate deposits, as I told you, the sedimentary rocks contain 82% of world's production. Their resources of about 2,200 billion tons. They are mostly from marine, and they are formed at great depths of more than 500 meters. Then there is second type of deposit about which people may be interested to know. It's called guano deposit. Guano is the bird excreta. The bird's droppings, very common, very famous. in Pacific Island. Like you have heard about the Christmas Island, or you have heard about the Nauru Island in Pacific. There are many atolls where the French people used to have their atom bomb and hydrogen bomb right. These islands are formed nothing but only but bird droppings, and bird droppings are all 100% P2O5. All bird droppings are P2O5. Over the years, 7 years accumulation, they have formed islands. So these are called Guano Deposits. Can you imagine that the entire island of Nauru is made up of guano deposit, and everybody just whenever they want to sell something, they dig in their backyard and sell it, because that is available, that can be sold to any farmer for utilizing it as a fertilizer. And then there are igneous rocks. Igneous rocks, like I told you, like alkali igneous rocks, they are also found in the form of a as a element P in different minerals. Next. As I just told you, repeat the same thing: sedimentary mineral deposit, igneous apatite deposit, bird guano deposit, metamorphic deposit, weathering-induced deposit. Next. Now, what are the types of sedimentary phosphorite? Sedimentary phosphorite deposits occur in the form of nodule. There is spherical concentrations that are randomly distributed along the floor of the continental shelf. You know what is the continental shelf? Continental shelf is in the just when you go to the beach and then you get into the shallow marine part, and then you start the continental shelf, which is again a steep deposit. So they are found in the continental shelf. Most phosphorite grains are of sand size. Sand size means about 0.03 to 2.3 millimeter, and they are many times they are greater than 2 millimeter. They are very rare. Larger grains are called nodules. Then you have bioclastic phosphate or bone beds. Bone beds like shark and very different type of fishes. They have all bones in their body. Especially shark and dolphins and other things, they have got very large bodies. And when they die, their soft part gets sort of destroyed by oxidation and other thing. But the bone gradually drops down to the sea floor, and there the phosphorus comes out of the bones, and you get phosphate deposit. Now, like for example in Florida, if you walk around the beach, you will get large number of bones. They're all strewn over on the beach. And those, if you just pick them up, they're nothing but pure phosphorites. They have totally been transformed from a bone to a phosphate deposit. So these are called bioclastic phosphate or bone beds. They are also formed by invertebrate fossils like brachiopods and other organisms. Third one is a process called phosphatization. The term is phosphatization, means the original rock is something else, but that has been invaded by a solution which has got rich in phosphorus. Like for example, there is a limestone or a calcium carbonate rock, and there is an over which a solution rich in phosphorus comes in. So it gets into these cracks and fractures and replaces the calcium carbonate and changes into a phosphorite rock. So this is called a phosphatization process. Next. Types of phosphate deposits, I just explained to you. They are sedimentary mineral deposits, they are igneous deposit, metamorphic deposit, organic depositing. The 75% of the world phosphate resources are won from the sedimentary marine phosphate rocks, and 15-20% from igneous rocks, and 1 to 2% biogenic sources, largely by bird and bats. So phosphate rocks refer to rocks containing phosphate mineral, usually a mineral which we call it apatite. Next. They form depositional environment which they are formed very shallow, near shore, with low energy. Because if there is high energy, they will be washed away. So in supratidal, the tides were, and littoral or intertidal. Now I think anybody who is aware of the coastal morphology, they will understand what these names mean. That estuarine is part of the estuary is next to delta, intertidal which are affected by the tides, and supratidal means away from the supratidal right up to the onto the land. And most important thing that it has to be low energy environment. Because if it is high energy environment, the phosphate grain will be washed off and go into the deep sea again. So it has to be low energy so that it allows the phosphate to precipitate from this water into a deposit. Next. Same thing, and I think repeat next, please. Next. The classification, when we classify these marine deposits, there are three types we classify. We call pristine. Absolutely pristine means which has got the very no organic material has been, no bioturbation has taken place. The world has, that means those organisms which are purely phosphatic rock, and these are called pristine. They are called condensed. Sometimes they are in the form of a laminae and the beds, they are called condensed. And then allophthenous, these mean when they have been transported from its place of origin and then redeposited in another place. You move from one place, they formed in one place, and they went again and transported and then get redeposited maybe a kilometer away, 2 kilometers away, or maybe 100 kilometers away. These are called allophthenous. Next. What are the minerals? The chemistry of it. The mineral is called apatite, is a general apatite. This is in almost literature you will find they use the term colophane. Colophane is now a discredited term, we don't use it. This term was used when X-ray crystallography had not started. So when X-ray crystallography started, people thought that these grains are colloidal minerals, colloidal material. But when the X-ray crystallography started, they found that they are not colloidal, but they are also crystalline, microcrystalline, and cryptocrystallines. So they found that there is a mineral called francolite, or also known as the carbonate fluorapatite. They are also called dialite when the percentage of fluorine increases to more than 1%, then they are called dialite. The fluorapatite, when you have the fluorine content is more than 2%, called fluorapatite. When you have the hydroxyl element into that, called hydroxyapatite. Now, all our bones, our nails, and everything, our body parts, wherever there are bones, they are all hydroxyapatite. They are all made up of hydroxyapatite. You analyze any bone of any part of your body, or your nail, you put it in analysis, you will find this is a carbonate hydroxyapatite. Then there are 3 or 2 minerals called trandolite, bevelite, and stendite. These minerals are made up of alumina. When the phosphorus is associated with alumina or by soil and clay, then these are called clay phosphorite, or what you call aluminous phosphorite. Next. This is elemental association. You can see here the iron hydroxide and PO4 is occurring here. There is a precipitation mechanism with carbon, organic carbon, and PO4 ultimately leads to formation of the francolite. So you have and they all form in a suboxic zone to partly oxic zone. And now in anoxic part, you have iron sulfide, which transforms it and moves it up to the suboxic state and then to oxic state, where they get precipitated. Next. This is the composition, the main structural composition. You get the composition mineral. It is called Ca10A minus B, Ca Mg, PO4 6 minus X, CO3 XYZ, CO3 FY, SO4 F2. Means calcium, part of the calcium is replaced by rare earth elements. Therefore, phosphorite is a very important rock for extraction of rare earth. You have also some like neodymium, strontium, they're all associated, they replace part of calcium. Similarly, sodium is not replaced much, magnesium is not replaced much, but PO phosphate is replaced by oxygen, so PO4 concentration changes. Then the carbon dioxide CO3 gets exchanged with different type of oxygen, Similarly, CO3, similarly, fluorine contents changes and sulfate contents changes. Similarly, strontium, uranium, thorium, they are all associated and they all replace part of these elements here. Next. Next. Now, this is how they look in the ocean bottom. In ocean bottom sediment, the phosphate grains look like this. And you can see their phosphate. You have heard about the manganese nodule mining. The government of India was trying to do mining from the Indian Ocean. Similarly, there are phosphate nodules associated with manganese nodule, which can be mined. But they are not economically feasible because they are found in the deep depth, in the deep sea, and it is not possible to sort of extract or economically from that depth. Next. This is how they look, how this phosphate looks under the microscope, scanning electron microscope. This is what we call the petrological studies. When we see the grains, you can see you can very easily see that they are formed by organisms. There are different tissues which you can find into these rocks. Next. Another scanning electron microscopy of the phosphate, you can see the different grains into that. Next. Again, another set of just to make acquainted how they look under the scanning electron microscope or under microscope. When we do our study, we try to differentiate between the different type of phosphate element, phosphate minerals into that, and also try to identify which type of organism is responsible for a particular type of feature, particular structure. Okay, next. The scientific problem is, we are coming to the end now. What is the mechanism of the phosphate formation? How the mechanism formed? What are the and why are the phosphorite distributed unevenly in geological record? As I told you just now earlier, that phosphate occurs right from the 2.5 billion years old rock to almost recent rock, but they are not found in uniformly everywhere. In some geological period, they are found in extensively, they be big deposits, and in some geological moment they don't form or they are very little, they form very little. Next. This is an event, there are the factors which control the phosphate deposition through time. If you see there is a middle line here. On the extreme side is the 4 gigayear, means that is the time when the earth originated, approximately little after the earth originated. And then come to 0 gigayear, the present day. In between, you have got about 2.5 billion years, 2.4 to 2.5 billion years. There is a line, vertical line, which is going right from top to bottom, you can see here. This is in geological term, we call great oxidation event. This is called GOE or great oxidation event. It has changed the origin of life and affected the origin of life greatly. So at 2.5, there was a sudden change in the chemistry of the ocean, sudden change in the chemistry of input from the land, and then there was a extensive occurrence of phosphorus into the sea. Before that, the phosphorus was locked up into the rocks and did not come out of the sea, did not form the sediment. But at 2.4, it started coming out, and gradually it changes. So they form red bed, they form oxide paleosols, they form phosphorite, they form just so on the entire scene. So this is the line which shows we call great oxidation event were responsible for the great phosphate formation. Next. This is the same thing, it's shown in a different way, where it is correlated with the different isotopes, like sulfur isotopes, iron isotopes, chromium isotopes, and other elemental relationship. Then in what way the elemental ratios also change at that particular to great oxidation event. Great oxidation event change the complete change. Like for example, in the top point, you can say the delta 34 SS, the sulfur isotope, drastically changed from that frame. If you can see on the right side, their vertical columns are extensive, while before that, it's very little. The sulfate is only in the seawater, but after that, they started depositing and formed sulfate deposits. Similarly, in the lower part, you can also see different elements, chromium and other thing. There is some they have included for the molar ratios. They were very high in the pre-oxidation event, and they became almost negligible after this oxidation event. Next. So this is a cartoon to show exactly the relationship between the iron deposition and the phosphate deposition. We know that in India we have got very big iron deposits in Kudurmukh area or in Nomandi area, in Odisha and other places in Par. They are all rich in iron deposits. Now, in different parts of the world also, similarly, there are very big iron deposits. So these lines, this red color, for example, this shows the peak period when the iron deposits formation. So what we find that after, if you see with the column 2,500, 2,800 to 2,500, and then right up to 1,800, 1,600, this is all red color. Red color is very prominent. There's iron rich and iron formation. And on contrast, if you see on the right side the the P25 peak is very small, very little. So during this period, this older period, the phosphate didn't form much. But as you come up, there's a period where there was nothing happened. This is what we call the Mesoproterozoic. This is also known as, in our geological term, called boring billion. The word is called boring billion because this 1 billion year of event in Earth did not show any change in isotope, did not change in the chemistry, did not change in the Earth. So this is called geologically boring because there is no event which took place between this particular period. So between, but immediately after the boring billion, you see on the right side, the yellow peaks are very prominent. CE, what you can see, series of these are the phosphate deposits. The big phosphate deposits are from in India. We have one big phosphate deposit in Mussoorie area in Himalaya, in Himalaya, Mussoorie and other places called like Nigalidhar and other places in that region in Himachal. And then we have a very big deposit of Precambrian time. That when you see the lower part in Proterozoic, is a one big deposit you have in India in Udaipur area called Jhamarkotra deposit, which is one of the biggest deposits. So you can see the youngest part of the art history has got large number of phosphate deposits, but the older part doesn't have. Now next. This is just to show you the global distribution of phosphate deposits in the world, different ages. The green color is for the Proterozoic or the Precambrian rocks. Then you have Cretaceous rocks. Then you have Tertiary and other places. One of the biggest deposits of the world is in the western United States in what we call the Phosphoria formation from California, right from the top, from Wyoming in the north, and right up to the Baja California, and then into the space, into the Mexico. This is a big deposit called Phosphoria formation. It is estimated that the total amount of phosphorus locked up in the rocks in Phosphoria formation is more than the total phosphorus present in the world ocean. The whole of the world ocean, the total amount of phosphorus that is found in the ocean is less than the total phosphorus which is locked in a rock as a phosphorite rock in the ocean. Some of the big deposits of the world are in China, in Mongolia, and in the Middle East in many places like in Iraq, Iran, and other places. And in US, there are, of course, in Florida deposits. And then in South America, you have the Peru, Chile, Brazil deposits. Like that. And in Australia, we have also very, very big deposits in the northern part. The billions of tons of phosphorites are available there. Next. Fine. So finally, we come to the last two slides called what triggers the ice precipitation. Why? Because, as I told you, phosphorus is a phosphorus is a trace element in seawater. if you see the quantity amount of phosphate in parts per million ppb level in the ocean water, but in spite of that, the phosphate forms in the sea. That means, and anything can precipitate only when there is supersaturation. So if something which is occurring in the ppb level is getting saturated into a phosphorus mineral, that means there has to be some mechanism, some chemical mechanism, or some organic mechanism, or some tectonic mechanism. So what we see, the most important process which help the phosphorus to form is called the plate tectonics. Plate tectonics is, I think, everybody knows now what is plate tectonics now. Now our distribution of different part of the earth is because of the plate movement. We have got an Indian plate moving north. Everybody knows about the Indian plate is moving north and colliding with the Himalaya, and Himalaya was formed by this method and all those things. So the plate tectonics is a process in different parts, which there are two ways you can do. You have a major tectonic, that means region-wise tectonic, that means maybe India plate moving into a Siberian plate, or in a North American plate into a European plate. But there are also local tectonics. Local means small distance. Within the, for example, within the Rajasthan, the Aravalli plate getting into the Delhi plates, Aravalli plate into the Punjab plate, or the Madhya Pradesh plate, a small plate, docking into the Bundelkhand plate. So they are local tectonic. So they are controlled by position. That means, what is the important thing? They have to be in a low latitudinal position. Most important thing is low latitudinal, because the phosphorus is formed in a warm condition and warm water, and warm water is available only in low latitude, and that low latitude is within about 30-degree latitude. That means, if you see the distribution of the earth into phosphorite, they are all concentrated along 30-degree latitude. They are neither found in the southern latitude, neither they are found in northern latitude. So all over the world. So latitude and location of the place. Then there will be regional upwelling. There will be formation of major seaways. That increases the rate of global oceanic overturn. Oceanic overturn means that the deep water phosphorus-rich material has to come up on the surface to form and get deposited. Because deep water is rich in phosphorus, where the phosphorus occurs in a dissolved state. The dissolved state material has to come up, so that there is a nucleation of those elements, and then the precipitation of those elements in the shallower water, where there is a warm shallow water, and warm shallow water causes the rise in the pH, and which allows the precipitation of the carbonate and phosphate. So there are also to be associated with the photic zones, because photic zones are the places where you have the organisms like cyanobacteria and the different organisms. They live only in the photic zone. So there are associations of photic zone, association of seaways, association of regional upwelling, local upwelling, association of carbon and phosphorus rich material, and all those things which is to form a phosphorus. Now all these things, all these points, when they join together, only then phosphorite form. Next one, last one. So you can say the climate change takes place, leads to sea level rise. What everybody is talking about nowadays, this must have happened number of times. This has happened in geological time hundreds of times. So climate change led to a sea level rise. Sea level rise led to trapping of the sediment. Sediment rise, they led to the reworking. Reworking means rehashing, and then they form the accumulations. Similarly, the local tectonics mean local earth movement. They form in the some basement heights, some sea mounts inside, and there is a local dynamic upwelling that increases the photic zones and biomass that ultimately form the calcium-rich, phosphorus-rich shallow water, and then finally ultimately lead to formation of phosphate deposit. That means what you see here, it is a big major chance. All these things have to trigger at one time. That means local tectonics has to be favorable, sea level has to have happen, the trapping of sediment must happen, the reworking must take place, the chemistry of the water should be the same, and only when all these factors together join, only then phosphorite will form. So is a chance, the formation of phosphorite is a chance. Only by chance they form, only when all these factors, they all factor together. Therefore, that is the reason why even the ppb level P in the sea, it finally form a deposit. That is the fate of P, which I described right at the beginning. That is the P which originated perhaps from a man's or human bone, leads to a formation of phosphate deposits, and that phosphate deposit will be used by the farmers to produce the superphosphate, and then give you a high yield of wheat and rice, and then you eat that, and then again the cycle goes on and on and on. Thank you very much. Next.
Thank you, sir, for delivering such a good talk on and apprising all of us about the phosphorus biogeochemical cycling and its relevance in today's time. And I just want to tell you all that sir has very well addressed the topic, and it is very much relevant for today because we all know that Earth planet is a finite system and has limits with respect to its resource base as well as its exploitation by humanity. And these safe operating limits are very well defined by planetary boundary concept of Earth. And as per the latest update, which is available on this planetary boundary concept, 4 out of 9 boundaries have already been crossed. Among this, the 4 are climate change, loss of biosphere integrity, land system change, and altered biogeographical cycling of nitrogen and phosphorus. And in that, it has been already mentioned that the upper limit for the phosphorus, anthropogenic phosphorus going into the ocean is around 11 million tons per year, and we are already putting up to 9.5. So we are very near to cross that limit, and to check ourselves, we need the full understanding of this phosphorus biogeochemical cycling. And on that, Professor Dhiraj Banerjee sir has very smoothly and very in a layman's language explain us that how is the biogeochemical cycling of phosphorus is taking place, what are the critical factors. So with this, sir, we are very thankful to you for delivering the talk for all of us. And thank you very much, sir. Swati, now I would like to invite for a formal vote of thanks to Ms. Swati Singh, the Program Officer of Jnu Envis Geodiversity. Swati, please.
Thank you, ma'am, for giving me this opportunity. I would like to formally thank Professor Dhiraj Mohan Banerjee, sir, for delivering such a in-depth and lecture. I think it has helped us understand the entire concept really from ashes to ashes, and a lot of think points for the young researchers in you given the future and the lacunas which are still there. So I think it would have really helped our lot of participants who are working in this area. Thank you so much, sir, for sparing your time and giving us this insight on phosphorus. I would also like to thank all the faculty members of our School of Environmental Sciences for participating in this event and making it a success. To all the participants from all over the India, your participation and your interest in these programs really encourage us. And I would like to thank my coordinator, Sir Professor Paulraj sir, for allowing us to organize this day. And since we all are working in the field of science, so this day as such is very important for all of us. Thank you, sir. Dr. Usha Mina ma'am, our co-coordinator. Ma'am, thank you for hosting and conducting the webinar so well. Thank you, ma'am, for the entire sessions. And last but not the least, my colleagues in Jnu Envis, thank you for their technical support and constant inputs. So thank you. It was a really nice and nice event, and especially, sir, we've got really lot of inputs and a new dimension we've understood. Thank you, sir. Thank you, everyone.
Thank you. Thank you very much.
So now we are ending the meeting. So
Okay.
Thank you, sir. Thank you.
Thank you. Thank you, sir.
Thank you so much, sir. Thank you. Thank you. Thank you. Thank you, Nanda. Okay,
Thank you, sir.
Thank you.
Thank
Very
you.
nice.
Thank you.